All right. Good morning, everyone. Today we're going to be looking at exponentials. In particular, we're going to be looking at exponential growth. So to kind of understand how exponential growth and exponentials work, we're going to start with an example. So exponentials are used to model things that increase or decrease by a multiplication. So we've seen a lot in the past, especially with, say, like lines, where they increase by, say, a constant addition. So say it costs $5 for each thing, then if we buy 100, we just multiply them together. And if we go from 100 to 101, we add 5 more. If we go from 101 to 102, we add 5 more. So exponentials has to do with multiplying each time. So let's look at an example here. So a type of bacteria grows such that it triples in number every day. On the day we first measure the amount, there are 100 bacteria. So we're going to use a table just this first time to help us see the numbers changing. We're making a little table of values. So we're actually going to start with day 0. So day 0, what's our population? So day 0 is when we do our first observation. So our first observation is of 100 population, 100 bacteria. And it's saying it triples every day. So on day 1, which would be 1 day later, it will be triple. So that'd be 300. Okay. And I'm just going to write how we got this off to the side here. So that's 100 times 3. And on day 2, a day later, well, it'll be triple again. So it'll be 3 times that, so 900. And that we could write as 100 times 3. That's how we got to 300 times 3 again. And you can see how we're repeatedly multiplying. So let's see that again with day 3. Multiply by 3 again, and we get 2,700. Right, so we could write that as 100 times 3 times, or we can use an exponent, and this is why they're called exponentials. So we could say that's just 100 times 3 cubed. And on day 4, we have 2,700 times 3 is 8,100. And that's just 100. Our starting amount times 3 to the power of 4. And on day 5, we'd have 24,300, which is 100 times 3 to the power of 5. So with these exponentials, we can really see the population grows really fast as it gets bigger. So it triples every time, but if we look at the differences, it goes from 100 to 300, that's a difference of 200. It goes from 300 to 900, that's a difference of 600. It goes from 900 to 2,700, which is a difference of 1,800, and it just keeps getting bigger and bigger. By the end, we have a difference of like 16-ish thousand between one day and the next. So it grows really fast the further you go. Okay, so a lot of things in nature follow this type of behavior, have this exponential growth. Okay, so we don't want to do these tables of values. This would be a lot of work to do for questions, to write out every single day. Sometimes maybe that's what we want to do, but we want to be able to represent it using a function. So we can represent this repeated multiplication as an exponential. So we might say the population, lowercase p, on day x is equal to, and we kind of were writing an equation over off to the side here. So it's 100 times 3 to the power of whatever day we want to know. Okay, so as an example, what's the population after 3.5 days? Well, our table of values isn't going to tell us 3.5 days. And how do we figure that out? Like, what do you multiply to go from 3 to 3.5? You can't triple. But is it like double? Is it 1.5? Well, the exponential can tell us. And that's the nice thing with exponential is we can plug in other decimals and things like that, and fractions, to find these answers for these times in between. So 3 to the power of 3.5. And your calculator can do a decimal exponent. And if we punch that in, we get 4,677 once we round. All right. So this is just a quick example so we can see the way this grows and see how we can get an equation to represent this. But we don't want to come up with the equation each time. We want all our equations for these styles of questions to look the same. So there's a general equation we use. So the general equation looks like this. F of x. Sometimes we might use like P for population or A for amount. Sometimes we replace the F part of it with something that's a little more question appropriate. And sometimes we replace the X with, say, T for time or something like that if we want to, but the form will always be the same. So it's always equal to A times, I'm going to use a dot for multiplication, B to the power of X. Okay. So note here, only the B has an exponent on it. And because of BEDMAS, we always want to do the exponent before we do the multiplication. Okay. So let's go over what each of these pieces represents. So f of x, well, that tells us the amount. In our previous question, it was the population of bacteria, or the amount of bacteria. So it's the amount after x growths. Okay. So it's the amount after x growths. And today all we're going to talk about is growths, but I'm going to write slash decays. And decays is something we'll talk about another day. Okay. So A is always our initial amount. So it's how much is there at the start on day 0 or at time period 0. Okay, so in our previous example, it was 100. That's how many bacteria there were when first observed, the initial amount. B is our growth or decay, if we're doing a question about decay, which we will another day, factor. Okay, so this is the descriptor mathematically as to how it is growing. So in our first question, it was tripling every time. So B was 3. It's the thing that's multiplying each time. Okay. We also have x is that's our exponent, and that exponent represents the number of growths let me write that a little neater. Number of growths or decays if we were to do a decay question. Okay. And there's actually a little equation we can use to calculate this. So in our example we did before, if I scroll up to it, it was the number of growths was the same as the number of days because it tripled every day. In our next example, it's not going to be every day. So sometimes we need to kind of calculate the number of growths, and it's really simple to do that. We have a little equation we can use. It's the total amount of time divided by the time for one growth or decay. Okay. So this is the general equation. Every question we're going to do is going to come back to this equation. Some questions will know different pieces of it and be finding other pieces, and we'll do more and more of that throughout the day. So let's take a look at how we can use it in our first question here. All right, so in this one, an insect colony has a current population of 50. The colony's population doubles every 3 days. What is the population after 20 days? All right. So when we're dealing with questions like this, it's a really good strategy to just write down everything we know and maybe put some question marks around things we don't know. If there's some things we can really quick calculate, we can write those in as well. So it's asking what the population is after 20 days. Well, that is our f of x. That's what we're trying to find. So we don't know that. That's what we're trying to find. We're trying to find the population after 20 days, at the end. It says that current population is 50. So that'd be our initial amount. That's our A value. A is 50. B, well, B is, remember, our growth decay factor. So how is it changing? Well, it says here that it is doubling. So that's 2. And X is our number of time periods, or number of growths or decays. In this one, it's growing every 3 days for 20 days. So our total amount of time is going to be 20, and each doubling takes 3 days. So X is going to be a fraction, and that's fine. We can plug this all in now. So F at 20 over 3 is equal to A 50 times 2 to the power of 20 over 3. Now, when you're plugging this in your calculator, you're going to want to be very careful. It's very common for calculators when you type fractions in for exponents to not do them properly. So if you use an fraction exponent on your calculator, make sure you put that exponent in brackets. So I'm going to do that on my own now. So I'm going to do 50 times 2 to the power of, remember, just the 2 has the exponent on it, not the 50. And then I'm going to open bracket, 20 divided by 3, close bracket. If you have a fraction button, you could also use that, but the fraction button won't necessarily mean you don't need brackets. It equals, and I get 5,079.6 something. And we're talking about insects. You cannot have a decimal of an insect. So we will just round up to 5,080. Okay. So that is how many insects. And we can write a little conclusion here. So therefore, after 20 days, there will be 5,080 insects. Okay. Let's look at the next part here. It says, when will the population be 1 billion? Okay, well, that's a really big number. Well, if we think back to the first question we looked at, we know that it grows really fast the farther we go along, right? The numbers get really big really quick. So maybe it won't take as long as we think. But let's find out. So let's write down the things we know, the things we don't know. So in this case, we know the final population. Fx is 1 billion. Put some commas in. It's easier to write it by hand like that. Okay. And we still know our initial amount is 50. It still grows the same, so B is still 2. But in this situation, X is what we're trying to find. The fact that it's asking when will the population, right? It's a time-based question. That usually is represented by X in our equations. So let's try this. Let's plug it all in. I'm going to try to squeeze it over a little bit because we're a little short on width here. So 1 billion equals 50 times 2 to the power of X. Okay, so we want to rearrange this. But I don't know how to get an X out of the exponent. And in fact, we don't learn how in high school until we take advanced functions. So we're going to have to deal with that on our own. So let's see how we can do that. Well, I know I can get the 50 over, so I can divide both sides by 50. That's at least something I can do. Right, these kind of cancel then. And I get 20 million. It's at least a slightly easier number to work with. Is equal to 2 to the power of x. And because we don't know how to rearrange from here, we're just going to guess and check. And we'll get an approximate answer. Okay, so to guess and check, you could just use your calculator, do like 2 to the power of 15. And we get a number. And I got 32,000. That's not big enough. So because we got a number that's too small, I want 20 million. I'm going to try a bigger number, maybe 2 to the power of 20. I got a million that time. Okay, that's getting closer, but it's still not big enough. Let's maybe 2 to the power of 25. And this time I got 33.5 million. So that's too big. So maybe I could do 2 to the power of 24. And I get 16.7 million. That's getting close to 20 million. I could maybe get a little closer. Maybe we'll do like 2 to the power of 24.3. Okay, so I got, that looks pretty good. I got just over, so maybe we could say 2 to the power of 24.3-ish is 20,655,170, and if I round 6. Okay, so that's pretty close. You don't need to get dead on. Just getting close is good. Okay, so that means that x is approximately, and I'm going to do some squiggly equal signs to show an approximation, 24.3. Okay, so let's think. Did we answer the question? When will the population be 1 billion? Well, x is 24.3, but that doesn't really tell us when. That tells us how many growths it's going to take, but we want to actually say how many days. Like we want a good unit of time. So we can look and remember that it takes 3 days for each of these to happen. So our days is going to be 24.3 times 3, because it takes 3 days for each double. And we can use a calculator and do that multiplication. We get about 72.9, 73-ish days. Okay, so we'll just say that's approximately 73. We're approximating at this point anyways, so we can do a little rounding. Okay, and lastly, so that's how many days. Let's just write a quick conclusion here. I don't have a lot of space, but I'm going to squeeze it in. So therefore, after about, so we should indicate in our response to the question that we've approximated. So you could say after approximately or after about. Okay. So just because you're approximate doesn't mean you don't have to be close. You still want to be close. 73 days. There will be 1 billion insects. Okay, so the only time we'll be guessing and checking is when we're trying to solve for an exponent. If you're trying to solve for anything else, we can use algebra we already know. Only when we're solving for exponents do we need to use guess and check. It's the only time that's okay. And we'll always get like an approximate answer. Maybe every once in a while we can actually get a perfectly accurate answer. Every once in a while that's the case. Yep. And that's about it for today. So there's a practice question underneath for you to work on.